All right, in section 4.1.6, we'll be calculating the definite integrals of polynomials. All right, so we're now ready to compute the definite integrals, the integral from a to b of f of x dx for polynomial functions f of x. We'll be using the following rules and formulas that we first saw in section 4.1.2. All right, so first of all, if you have the sum of a sum of two terms, you can split them. You'll get two different sums still from k0 to n. So the bounds of your sum, of your summation do not change, but you can split the terms and do one at a time. All right, second, if you have a c that's common to all your terms, you can factor it out. And this is what you get. We also saw that if you add 1 again and again, you'll get n. If you add k again and again, you get n plus 1 over 2. If you add k squared, you'll get n plus 1, 2n plus 1 over 6. And k cubed, we said, was just a square of k. And there you go. All right, so let's see how we can use this to evaluate an integral. All right, so I want to evaluate the integral from 0 to 2 of x squared. So let's identify our different pieces. From this formula here, you know that a is 0. B is the top bound, that will be 2, and my function is x squared. Right, so we have a formula for delta x, so we don't actually need to sketch anything. We know that that's 2 over n. We have a formula for xk, it's a plus k delta x. So now it's 0 plus k 2 over n, it's 2k over n. So if you remember what our formula was for Sn, great. If you don't, I'll remind you right here. So summation from k equals 1 to n, delta x, f of xk. So what I'll do first is I'll look at this piece and I'll simplify it. I'm going to simplify this as much as possible before I introduce the sum and the delta x. All right, so f of xk in this case, that's just a xk squared. So whatever I have here, I square. So I'm going to square my xk. And so 2k over n will get squared. I have 4k squared over n squared. All right, so that's going to be the height of my rectangle. That will be the width. All right, so when I compute the approximation using n rectangles, I'll have width 2 over n, I'll have height 4k squared over n squared. And so my whole approximation will be this sum right here. Now I want to use the formulas above to evaluate this. So I want to simplify it until I get sum of 1, sum of k squared. So now I'm going to take all of this, which doesn't depend on k, and I'm going to be able to pull it out in front of the sum. So I'll get 8 over n cubed, summation from k equals 1 to n of k squared, and that is going to be this formula right here. So n plus 1, 2n plus 1 over 6. So I want to take the limit of this. So before I put the limit, I'll simplify it. I'll put the constants in front. So I had 8, 6. That becomes 4/3 when I cancel the common 2. And then I have 3 terms here, and I have 3 n's here. So I'm going to place them, I'm going to pair them up like this. And I'll divide. So I'm going to get 4/3 times 1 plus 1 over n. times 2 plus 1 over n. And you could see, hopefully, that if I read it in this way, taking the limit, which is what I need to do next if I want to compute the integral. So if I look at this limit, that's going to be the limit as n goes to positive infinity, 4/3, 1 plus 1 over n, 2 plus 1 over n. And if I plug in infinity, I'll get 1 plus 1 over infinity, 2 plus 1 over infinity. I'm going to get 4/3 times 1 plus 0 times 2 plus 0. I'm getting 8/3. All right, so what is this 8/3? Well, if you look at the graph of this function, so it's going to look like this, y equals x squared. And if you look at the parts from 0 to 2, then what we've computed is this area right here. All right, so this is an area that we were not able to compute before this. It's not a square, it's not a triangle, it's not a rectangle, it's a new area. It has a curve for one side. In fact, this function and this area is what Aristotle started thinking about when he thought of using these rectangles and approximating in this way. And that was kind of the precursor to the integral that we're using today.